Hi, my name is Amadeus and I'll be sharing about my final year project, which is about an interpretable fuzzy embedded deep neural network and its application in stock trading. Here's an overview of the presentation. Let me start off by explaining the motivation for the project. We all know that neural networks have the capability to form accurate predictions, commonly in regression or classification problems. However, neural networks are essentially a black box, thus there's a lack of interpretability, which is not acceptable for high compliance applications like financial management. To resolve this, we look into fuzzy inference systems, which are able to model complicated logic as linguistic terms that are easily understood by humans. Thus, by combining fuzzy systems with neural networks, we basically incorporate human linguistic terms and are able to achieve both the high accuracy of neural networks as well as the interpretability of fuzzy systems. With that, we have the fuzzy embedded long short-term memory architecture, or FE-LSTM. This is a parallel architecture where the embedded deep learning structure, which is a LSTM in our case, lies parallel to the fuzzy rule generation. The FE-LSTM is inspired by a Mamdani-type fuzzy inference system. As we can see from the architecture, both the LSTM and fuzzy rule base share the same input and output linguistic. We will examine how this helps in improving interpretability later. The FE-LSTM consists of 5 distinct layers. First, we have the input layer that simply receives the input data and passes it on to the next layer. The second layer is the antecedent layer. This is where fuzzification of the input features is performed. The DB-stream clustering algorithm was used to cluster each input feature independently in a localized approach. Thus, each input feature will have its own set of clusters, with each cluster representing a fuzzy membership function. These membership functions are used to fuzzify the input features. Our third layer comprises of the parallel inference and rule-based layers. In the deep learning inference path, the LSTM maps the fuzzified inputs to fuzzified outputs, while the fuzzy rule base maintains the set of fuzzy if-then rules, with each rule being assigned a Hebbian pseudo-weight. Next, the fourth layer is the consequent layer, which represents the consequence of the fuzzy rules, where each consequent node corresponds to a fuzzy membership function of a target output feature. Lastly, we have the output layer, which performs defuzzification on the fuzzy output values to obtain a crisp value for each output feature using the center of area defuzzification technique. But how exactly does FE-LSTM achieve interpretability? This is achieved with fuzzy rule tagging. Each data point fires a fuzzy rule determined by the winning clusters of the antecedent and consequent. The Hebbian weight of the fuzzy rule is then increased each time it is fired. Each fuzzy rule is then tagged to a set of corresponding neurons that have an average activation value above a set threshold when the rule is fired. Thus, the system is no longer a black box, as we are able to inspect each rule fired and determine the corresponding neurons associated to the rule. We benchmark the performance using actual stock time series dataset, which include the S&P 500, FTSE 100, and the CAC 40 index, predicting future stock prices from T+1 to T+12 time step. We also use Monte Carlo evaluative selection for feature selection, as well as genetic algorithm for hyperparameter tuning. Each stock dataset consists of historical prices from the year 2000 to 2022, and we split it 70 to 30 chronologically for training and testing. As seen from the results, the FE-LSTM roughly suffered between less than 1% to around 5% drop in Pearson's correlation coefficient value compared to the vanilla LSTM. However, by sacrificing a bit of prediction accuracy, we were able to make interpretable predictions by inspecting the fuzzy rule base. As seen from the figure, we are able to determine the top fuzzy rules and their pseudo-weights. Finally, we apply our FE-LSTM in stock market trading. We will be using MACD, which is a popular trading technical indicator for detecting trend reversals. However, it is a lagging indicator as it uses moving averages. To reduce the time lag, we will make use of the forecasted prices from FE-LSTM and integrate them into the moving average computations as shown in the equations. Therefore, we will have obtained a predicted MACD that utilizes forecasted prices. In order to trade individual stocks, we use the Advantage Actor Critic or A2C reinforcement learning model as it can handle a continuous state space. Here we utilize our predicted MACD values as part of the state space, and the A2C model can either choose to buy, sell, or hold its current position. To train the reinforcement learning model, the reward is set to be the total multiplicative profits. For each index, we train separate A2C models using the perfect MACD, which uses actual future prices, the predicted MACD, and the vanilla MACD. The perfect MACD model performs the best since it's most likely to give the most accurate trend reversal signals. Our predicted MACD model was able to beat the conventional buy and hold strategy, except for the FTSE 100 index. However, to reap diversification benefits, we do not want to simply trade only individual stocks. Therefore, we want to manage a portfolio to maximize profits and minimize risks. So, the Deep Deterministic Policy Gradient or DDPG reinforcement learning model is used to rebalance a portfolio comprising of 3 different stock indices. The actions of the RL model is the portfolio weights to set for each index, which should sum up to 1, and the multiplicative profit is used as the reward. Our results show that our RL model was able to outperform the conventional buy and hold strategy. To conclude, we developed FE-LSTM, which was able to achieve both high accuracy and interpretability. We then applied it to stock market trading and the portfolio management, and was able to beat the buy and hold strategy. However, there are still areas for improvement. Firstly, we can further develop our system into a live trading setup with online learning. Next, we can incorporate additional useful features like sentiment analysis to further improve prediction accuracy. And lastly, we should also consider exchange rates since we are trading between different international stock markets. And this is the end of the presentation. Thank you.